Hello and welcome. My name is Michael Grabowski, Product Marketing Manager at eSOL, and today videocasting from Düsseldorf, Germany. In this webinar, I would like to talk about Amdahl's law, why it plays a much bigger role in today's embedded software development than it has in the past, and how a modern RTOS can help here. Embedded software is developed on embedded hardware chips. For high-performance computing, developers must develop their applications on multi-core hardware now. Applications such as control units for autonomous driving, machines and robots for factory automation, or computer hardware for data centers. But why can only multi-core chips be used here and not just single-core chips? Every software developer knows that multi-core hardware doesn't make software development any easier. So why do we need to use multi-core hardware today? Let's start with Moore's law. Moore's law in a nutshell means more and more transistors on a single chip. More precisely, Moore's law describes the trend that the number of transistors on a chip doubles every 2 years. At the same cost. This rule still applies after 50 years. The problem? We can no longer use its advantages as well as we used to. Why? Because we need to consider two other important trends as well. The main cause of this problem is the Dennard scaling, or better, the end of the Dennard scaling. In the past, this rule describes the trend that the power density and thus the heat dissipation remain constant with each new semiconductor technology. However, it has not been possible to reduce the constant leakage current of the small transistors any further since about the year 2006. Since then, the CPU frequency can no longer be increased because the leakage current is already equal or even greater than the working current, which leads to major temperature problems. Most processors therefore reached a maximum of 4 GHz and only for a short time. This led to the question of whether a larger CPU with the same clock speed could be improved to such an extent that its processing power would increase. But the next rule applies here, Pollak's rule. It describes the fact that the number of transistors in a single CPU cannot be increased arbitrarily to obtain more computing power, because the more transistors there are, the more complex the CPU becomes, and greater complexity again reduces the performance of the CPU. As a result, a CPU twice as big only brings plus 40% performance, but doubles the size and power consumption. So there is a systematic barrier here as well. The answer to all these three rules was multi-core systems. With multi-cores you can use simpler CPU architectures to comply with the Pollak rule. To accommodate the end of Dennard scaling, two CPUs at half the frequency were used instead of one CPU at twice the frequency. The idea was that two CPUs could deliver the same performance as a single CPU, but at half the speed. Or 8 CPUs with the same performance, but only an eighth of the speed. However, the multi-core architecture also poses completely new challenges for the embedded software developer. Let's examine, as an example, a high-performance computer for autonomous driving. The chips themselves integrate many heterogeneous cores, performance cores, security cores, and other computer accelerators such as general-purpose GPUs, accelerators for neural networks, image signal processors, video codecs, and dedicated security IPs. All CPUs must communicate with each other and with the integrated accelerators. For functional safety, you need at least a dual-chip solution with fast communication between the chips. And for a complete autonomous driving system, the HPC ECU must communicate with other ECUs like the steering and braking ECU. How will the software applications communicate with each other in modern software-defined architectures? The application software is based on a service-oriented architecture in which clients, servers, and workers must communicate a lot and quickly. Some of these applications, such as decision-making and autonomous driving, are relevant for functional safety. For embedded applications, for example in a car with a speed of over 200 km per hour, at least in Germany, the system must be deterministic under all circumstances in order to avoid unforeseen conditions. A safety-certified real-time operating system, RTOS, must therefore be used. However, such an RTOS must be optimized for heterogeneous multicore and many-core chips, because this RTOS must enable the super-fast communication and at the same time maintaining the deterministic behavior of the system. While Moore's law is very popular and has been reaffirmed every year for the past 50 years, many software developers are not aware of a law that is much more important to them today. Every software and hardware developer learned this during his training, but it seems that most of them have forgotten it during their daily work. Let's start here with a small example. Let's assume that there are 4 cores and the application consists of only 4 mathematical formulas. In the diagram, these formulas are called threads, and each thread runs on a dedicated core. If all these formulas, threads, are independent and can be run completely in parallel, then the complete application with these 4 formulas has an accelerating factor 4 compared to a single core. Such an application has a parallel portion of 100%. If each of these formulas requires the result of the previous formula running on a different core, no speed increase will be seen compared to a single core. Such an application has a parallel portion of 0% because no function can do anything in parallel until the previous function has returned the result. The execution of these subsequent functions is blocked until the result of the predecessor is available. Now, finally, we come to the 4th rule, Amdahl's law. Amdahl discovered the connection between the parallel portion and the acceleration on multicore hardware. An application with 100% parallelism also achieves 8 times the speed with 8 cores. However, if it only has 80% parallelism, it only reaches about 3 times the speed on 8 cores as on 1 core. With just 15% more parallelism, in total 95%, the speed up at 8 cores would be already 6 times, much closer to the expected one. Small changes to the parallel portion lead to a very large effect at the speed up. With more cores, such as 16 and 32 core hardware, this effect becomes stronger and stronger. Let us now consider the implications of Amdahl's law for embedded real-time operating systems. Parallelizing can be realized on different levels, each with its own benefits and restrictions. Application programmer can use fork join libraries like POSIX threads, pthreads, Open Multiprocessing, OpenMP, or Java concurrency. But most human developers are not so good to regard all complex side effects of parallel computation. They can use instead dedicated software tools for source code parallelizing at the second development step. On the lowest software level, compilers can help too, but they don't provide an optimization for the used multi-core hardware configuration. Compilers are best optimized for general optimization of smaller sections of the source code. And on the hardware level, dedicated hardware IPs like GPOs or NNAs can help to enable fast computation of dedicated algorithms. Very, very helpful, but only for dedicated general algorithms or data processing. But all these optimizations are offline optimizations and can't help at parallelization in real time and high dynamic application scheduling. Dynamic performance load optimization can just be handled at the level of embedded RTOS and hypervisor by its thread scheduler mechanism. It can react online to any situation and optimize the load balance of all cores. Furthermore, it would be the most efficient way for software integration because the integrator will be supported by the RTOS to parallelize the application at each integration step. He or she don't have to take care about each possible core load situation, but understand and set the configuration of the RTOS scheduler. The communication of multi-core application of 3 processes is shown here. To make it easy, process A and B consists of only 1 thread, while process C consists of 2 threads on different cores. Process C is waiting for the data from both processes A and B. Thread 1 will communicate with thread 3, and thread 2 will communicate with thread 4. Most developers expect a timing that looks something like the ideal one shown here. Thread 1 and 2 each communicate independently with thread 3 and 4. To make it easy, let's consider the fastest possible configuration of a standard microkernel RTOS, a so-called SMP, symmetrical multiprocessing configuration. But here is the problem with today's microkernel RTOSs on multi-core hardware. To maintain the necessary determinism with traditional operating systems, the other cores are blocked during inter-process communication, IPC. Cores are prevented from executing further IPCs themselves, and in addition, thread states may no longer be changed on all cores. The latter means that a waiting thread cannot be put into a running state. Therefore, all other cores, even those that do not want to communicate, can run dry and thus also stop. Without this block, these cores would change the system status without the communicating cores noticing. The problem was caused because microkernels were designed and optimized primarily for single-core MCUs over the past century. Only after the global kernel lock has been released can the next IPC be processed, and this will reblock the system again. Here's the real timing of an SMP RTOS in detail. Thread number 1 starts a global kernel lock and prepares the message for the IPC with thread number 3. At the same time, the immediately following IPC request from thread 2 is blocked. After kernel lock number 1 is released, thread 3 starts global kernel lock number 2 to perform thread 1's IPC. After kernel lock number 2 is released, thread 3 can process the message from thread 1. At the same time, thread 2, which was waiting up to now, starts a global kernel lock number 3 in order to prepare the IPC for intercommunication with thread 4. After kernel lock number 3 is released, thread 4 starts global kernel lock number 4 to perform thread 2's IPC. After processing kernel lock number 4, the system can process new IPCs. In an automotive adaptive autosar application, at least 40 processes, each with 4 to 10 threads, are the foundation of a user application. All these 40 processes must communicate with each other. Therefore, lots of IPCs will occur during runtime. Regarding Amdahl's law, the parallel portion of an application will be reduced and thus the speed up on this 4-core hardware. Let's come to the solution for this problem. Let's start with a look at the development of operating systems in different segments. In the beginning of the data centers there was Unix, which over the time was replaced by Linux. Therefore, the problem of blocking operating systems in data centers has long been known and was solved a long time ago by so-called multi-kernel operating systems. Today, the big data centers like Fugaku run with a combination of Linux and multi-kernels like Mac kernel, Fused OS or MOS. The Linux-Android combination dominates the market for smartphones today. However, Google and Huawei are already developing their own microkernel RTOSs, such as Fuchsia or Harmony OS. And their development teams are already thinking out loud about multi-kernels on the internet. Let's go to the embedded world at the automotive, industrial or medical segment for safety-critical application. It all started here with a small RTOS such as a while loop, but today most devices run on a microkernel RTOS. This was fine even in the age of small MCUs with single or dual core architectures. In the age of heterogeneous, multi-core and many-core hardware, however, only a multi-kernel RTOS can provide the required parallel performance with low latency and freedom from interference. eSOL's RTOSs have gone through the same evolution. In 1986, eSOL launched its first RTOS for single-core CPUs. In 2006, we released the first commercial multi-core RTOS for the first multi-core CPUs produced by ARM. In 2012, eSOL was the first company to develop a multi-kernel RTOS. In 2019, it was equipped with a hypervisor option and was used for the first time on a core rate chip with 256 CPUs. 256. Multi-kernels have been specially developed and optimized for use with multi and many cores. In contrast to conventional SMP operating systems, which manage multiple cores through a single operating system, each core has its own independent microkernel, which is connected by high-speed messaging, but acts as a single operating system. If an IPC is carried out with a different thread on a different core, only the cores involved are temporarily locked locally. All other cores and their IPCs are not affected, and the determinism of the overall application is retained. These kernels can exchange IPCs completely independently without blocking other kernels. The parallel portion of the total application is increased. In addition to the acceleration, we will also gain greater freedom from interference, because thread communication on dedicated cores does not affect threads on other cores. More functional safety with more accelerating. The timing of the same application on the multi-kernel RTOS eMCOS looks completely different than on a standard microkernel RTOS. Thread 1 starts a local kernel lock on core 1 and prepares the IPC with thread 3. After only a very short acknowledge time, thread 3 starts a local kernel lock on core 3. The IPC between thread 1 and 2 is processed. After a short time, thread 1 unlocks the local kernel lock and thread 3 too, only a short time later. The IPC between thread 2 and 4 is carried out at the same time, completely independently in parallel. This is much faster and closer to the ideal timing. Indeed, there is roughly a single kernel lock duration instead of 4 kernel lock durations. With this, eMCOS multi-kernel RTOS can increase the parallel portion of the complete embedded application, let's say by 15%. Can you measure it? Yes, you can. Here we are running an application on a quad-core SoC with 1.5 GHz. While the task switching time of the SMP operating system increases from 2.4 microseconds to 3.4 with the use of more cores, the multi-core eMCOS remains continuously at 1.8 microseconds. We compared the IPC improvement at eMCOS with Linux and benchmarked the communication overhead. The results? eMCOS is 3 times faster within a thread on a single core, 4 times faster between threads on a single core, and 34 times faster at inter-core communication. Today's applications that were developed on RTOSs with old microkernel architecture have a reduced parallel portion. That wasn't a problem with a single core and not a huge problem with dual cores. However, if you are using quad or more cores, you will never see much accelerating with such RTOS architectures. If you can increase the parallel portion on an 8-core system from 80% to 95%, you would see an acceleration of 80%. That means with only 14% improvement in the parallel portion, the computing power would almost double. At a 32-core hardware, the difference would be already factor 3. Why is the eMCOS RTOS platform the right solution for your next embedded application? Does this mean that software developers who previously developed on a standard microkernel RTOS need completely new knowledge in order to be able to use the eMCOS multi-kernel RTOS? No, because eMCOS interfaces are based on the API standards most frequently used in the RTOS world. POSIX, and especially in the automotive world, AUTOSAR Scalability Class 1 and 3. Therefore, developers can take advantage of higher performance and freedom from interference based on the same RTOS API they have already been using. The most common use case of our eMCOS customers is that they start prototyping on Linux and then port their POSIX applications to eMCOS to ensure real-time and functional safety for mass production. By using eMCOS, you get the benefits of a pre-certified safety RTOS with a much higher parallel portion than a standard microkernel RTOS. eMCOS AUTOSAR is already certified to automotive ISO 26262 ASIL-D, and eMCOS POSIX ASIL-D certification is ongoing, planned to be finalized until the end of this year 2021. Since eSOL has been selling its own single microkernel RTOS ET kernel for a long time, our support teams know both words, microkernel and multi-kernel, very well for years. They can help you which RTOS architecture is the best solution for your individual application. If you have any other questions or comments about this videocast, please contact us via web, email or phone. Thank you for your time and stay safe.